Today we're going to talk about conductors, insulators, and polarization. The first thing you need to know is that electrons don't behave the same way in every type of material. Electrons in a piece of wood are going to behave differently than electrons in an aluminum Coke can. And we can separate materials into two broad categories. Some are conductors and some are insulators. They both have properties that are really important to understand charging beyond charging by friction. So let's first take a look at conductors. So some examples of conductor would be things like metal. Anything that's metal is usually a conductor. Water is usually a conductor. And since people are mostly water, people are actually conductors as well. Sometimes that's a good thing, sometimes it's not so good. So what is a conductor? A conductor, if we were going to define conductor, a conductor is a material that allows electrons to flow freely from particle to particle. So material that allows electrons to flow freely from particle to particle. Something like a metal, it's a great conductor. Most metals are great conductors. Sometimes a metal is described as being a nucleus surrounded by a sea of electrons. So a nucleus surrounded by a sea of electrons. And just that visual should help you understand why metals make great conductors, why metals allow electrons to travel so easily from particle to particle or from one metallic object to another metallic object. Insulators, on the other hand, are different. Some examples of insulators might be rubber, glass, wood, anything that's made of wood, or air. Air is actually a very good conductor. A very good insulator. So an insulator is defined as a material that impedes or inhibits the free flow of electrons. From molecule to molecule. Or atom to atom. And this is because each electron is firmly, I spelled firmly wrong, I'll fix it, is firmly attached to a particular nucleus. So imagine in a metal that's just a bunch of nuclei in a sea of electrons. In an insulator, each nucleus is firmly holding on to its own electrons. They're not being shared, they're not able to move around. Okay? So what happens and how we charge insulators versus conductors is going to be a very different process. So let's talk about polarization. And this is something that's a word you've heard and probably used in different contexts. But in physics and in the realm of electrostatics, it means the process of separating opposite charges within an object. So the process of separating opposite charges, so positives and negatives, within, I think I spelled within wrong, within an object. And by the way, in general, we're talking about a neutral object. Okay, that's a key point. So the positive charges become separated from the negative charges. What this means then is that one side of the object is left with an excess of positive charges. So excess just means too many. And the other side then is left with an excess of negative charges. Okay, so in polarization, we have a neutral object, but we've gotten all the negatives, and not all, but a lot of negatives, to move to one side or the other. And this process is going to look different in conductors versus insulators. So, for instance, we've got four rectangles here. And on the left, I have a conductor, and on the right, I have an insulator. So what we want to do is we want to draw the charges before and after a charged rod is brought near them, because that's how we're going to polarize an object. So let's go ahead, and before we bring and we're going to have a negative rod, as you can see down here. Before we do that, let's kind of give an idea of what the charges might look like. So I'm going to draw them kind of organized, but in general, they're really not. There's really no rhyme or reason. There might be a bunch of negatives here. There might be a bunch of positives here, right? They're negative, positive, negative, positive, positive, negative, positive, negative, kind of randomly put around. And let's stick with the conductor for a second here. And then let's realize that when we bring this negative over to the conductor, this negatively charged rod, all of the electrons that we had up here, and when I say all, I just mean kind of all that I'm showing, because we never get all of the electrons to do anything. But the electrons over here are going to move away from this negative rod. So that's going to look like I'm still going to have the positives, because remember, the positives can't go anywhere. So the positives are all going to stay where they were before. So you can copy and paste, but I haven't figured out how to do that in the app that I use to make the video, so I'm left with writing them down. But then the negatives are going to pile up over here. So let's, I want to make sure I'm even. So I got 2, 4, 8, 9, 10, 11, 12 negatives. So I'm going to put them all on the right side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you can see that the electrons have moved to the right to get away from that negatively charged rod. The positives couldn't go anywhere. The protons are stuck. But you can see now that we have more of a more positive side over here. So this would be the positive side of the large rectangular metal object, and this would be the negative side of that object. So this object is now polarized. The object up top here, this is neutral, this is neutral, this is unpolarized, and this is polarized. Now, let's go ahead and let's take a look at what happens with an insulator. An insulator is similar, and again, it's going to be kind of random for how everything is set up. So I'm going to go ahead and put positives and negatives, positives and negatives. I'm going to undo that. I want a negative there. And I change it around, and I got, maybe I even got positive, negative like this, positive, negative like this, negative, positive, negative, positive, right? All kinds of stuff, positive, negative, positive, negative, negative, positive, positive, negative, like that. Kind of random. And then I bring a negatively charged rod over to the insulator. Now, here's the difference between conductors and insulators. In an insulator, the negative charges are stuck. So, for instance, these guys are stuck together, and these guys are stuck together, and these guys are stuck together, and these guys are stuck together. You see the pattern. So this negative charge here cannot move over here. And this negative charge here cannot move over here. But what can happen is they can reorient themselves. Because the reason this is a positive charge and a negative charge, think of this as being a molecule. And one side is kind of more positive than the other because there's a bunch of electrons that are all kind of on this side of the atom. And this one right here, this side is positive, this side is negative, because a bunch of the electrons are just kind of hanging out over on here on this side. So when we bring this negatively charged rod over, all the positives and negatives have to kind of stay together, but they've reoriented so that the positive charge is on the left side and the negative charge is on the right side. So what we get is something that looks like this. So that all the positives side of one molecule are to the left and all the negative sides have gone to the right. So we still end up with this being the positive side of the object and this being the negative side of the object. It's still polarized, so this is still a neutral object. So we definitely want to say this is still neutral. This guy is neutral. They're all neutral. But these guys on the bottom are polarized. And you could see if we gave kind of a strength, I would think that this guy is more kind of strongly polarized. And when I say this guy, you can't see what I'm pointing. This guy is more strongly polarized than the guy over here on the right. Okay, so there's a little bit of difference into how that works. Okay, so that's the basics of conductors, insulators, and polarization.